Knife making in its most simple form is a repetitive series of steps. And it's easy to teach a man to master each step and go on to the next. What I find impossible to teach is an understanding of what the knife truly is. And if we analyze a cutting edge, and if we're aware of what's going on in the modern world, we realize how universal a cutting edge is. Some people view it very lackadaisically, very prosaically. To me, the knife is a supremely useful tool. It's a very honorable thing to be doing, making knives. It's very traditional. I sometimes think that the first specialist among prehistoric men was a man who ran across a bed of obsidian and reached down and picked up a sharp piece and realized, because perhaps he cut his finger on it, that was a useful tool. And he developed his talent at flaking flint or obsidian, and suddenly, bingo, we had a knife maker in that tribe who was so good at it that he could swap his labor of knife making for the other guy's labor of going out and hauling in the meat or harvesting the potatoes or something. So knife making in that sense is among the very earliest of vocational areas, the very earliest of craft. Because after I made my first knife on the ship, my God, I thought I'd died and gone to heaven. All of a sudden I had created something that was so bloody useful where there had been nothing before, and I did it. It came out of my hands and my mind. And I've been very happy as a knife maker. I'll be a knife maker until the day I can't be anymore. It's really important when we're working with steel to keep in mind how hazardous this work can be if you're careless. These grinding machines, most of them run at about 1.5 to 2 horsepower, and they'll eat fingers if you happen to get the fingers in the way. You have to be aware of what you're doing in the knife shop all the time. If Mother's going to come out and tell you supper's ready, the first thing you do is shut down. You don't try to run a machine while somebody's talking to you. If you've got visitors in the shop, you don't try to do your work on the grinding machines or on the drill presses or anything and keep a conversation going. It doesn't work. If you get distracted in this work, the price is fingers gone and so forth. This big 1272 is the strongest grinder we have in the shop, and we use it very respectfully. The grinders are hazardous. Probably the most hazardous machine is the buffer here. If it's used carelessly, it can jerk the blade, a piece of steel, out of your hand and sometimes throw it right at you. Now, you'll notice that the center line of this grinder is pretty high. The way you use a buffer in polishing steel is, the way we do it here, is to stay under the middle center line of the buffing wheel, like that. So that if the rag wheel jerks the blade out of your hand, it's going to throw it away from you. If you're working up here above the center line and it jerks it out of your hand, and this will happen, it always does, it can throw it toward you. There have been 2 or 3 knife makers who have had very serious injuries from buffing machines alone. Now, we told you the buffer was dangerous in the grinders. Equally dangerous is a drill press, and every knife maker either has one and uses it or is going to have to sooner or later. The drill press is a dangerous machine. It's hurt people probably for the last 100 years in mechanical shops. There isn't a man alive that can hand-hold a piece of steel and try to go through it with a 3/8 inch twist drill. About 1/4 of an inch is about the limit. Beyond that, you want to have your work solidly clamped on the drill press table before you turn it on. If you're trying to hand-hold a piece of steel while you're drilling with a big drill, inevitably, as you start to break through the bottom surface, the drill is going to catch the steel and start turning it. And then it's just a big, round, rotating, slicing machine. That's why we clamp our work. The drill press is dangerous. as are the milling machines or the lathes or any other machine that rotates under power. They're all dangerous, and you have to be careful when you're using them. This is no job for an amateur, and it's also no job if you're accident prone. If you're always looking for an excuse to get some sympathy from mama, stay the hell out of a knife shop. Now we're going to start the process of actually making a knife. And we're going to use probably the most popular knife this shop has ever made. It's the 4-inch drop hunter. This is the pattern, came off the pattern board, and this is a piece of steel. We're going to put it on the piece of steel, and we're going to clamp it in place. Now, for several minutes now, it's very important that we keep this piece of steel very well clamped so that it doesn't shift. And we're going to go over here. We've got a vise set up with horizontal jaws rather than vertical jaws. We're going to clamp it up good and scratch our line around it. I want to also point out that we're using a carbide pointed scriber here to get these lines. An ordinary steel scriber will not hold up to even one pattern. It goes dull in a hurry. That's why we have to use a carbide scriber. The back half of the pattern is scribed. Now we'll scribe the front half. And what you end up with is a picture of the outline of the knife on the piece of steel. Now we're going to take the clamped up pattern on the piece of steel over the drill press, and we're going to drill the fastener holes in the thong tube hole. These drills are pretty small drills. The fastener drills are actually less than a 3/16, and the thong tube hole is slightly less than a 1/4 of an inch. So it's possible, when you're careful, to hand hold them. And now we're going to ream these holes for precision hole size. Now we're going to ream the hole to size, and this is a precision reamer. And when you're reaming, you can generally tell whether the reamer's cutting properly or not. If it's not, the reamer's dull, you need a new one. Now we have the pattern scribed and the holes in the tang drilled and reamed to size. At this point, we're ready to take this clamp off. Now we're done with the layout of the pattern and drilling the fastener and thong tube holes in what's going to end up being a knife. Now we're ready to start grinding this picture we made on a piece of steel. To do that, we're coming to this big 1272 grinder. And because breathing steel dust isn't particularly healthy or pleasant, we're going to put a mask on, and we're going to put a magnifier on, because what we do here determines whether or not we end up with a successful 4-inch dropped hunter. Oh, yeah. Right. right, at the end of this grinding process, we've ground the knife to outline, to the layout lines, and we now have the definitive controlling shape for the 4-inch dropped hunter. You've noticed that I've been wearing a magnifier while I've been doing this job. That's because it's easy to go past the line or not come all the way through it, not come all the way to it, and if that's the case, then you don't have what we're aiming for, the Loveless 4-inch dropped hunter. And that's the reason for the glasses and working close and so forth. A lot of work yet to do, but what we've done just now determines whether this knife is shaped properly at the end of the job. Now we're going to do the layout work to guide our grinding operation. We want to have a precise set of lines down the center line of the blade, exactly 25 thousandths apart, centered on the vertical center line of the blade. So to do that, we have to know how thick the blade is, and it turns out it's 201 thousandths. So we simply go to a little pocket calculator. We put in 201 and we take out 025, and we end up with 176 divided by 2 is 88 thousandths. We go to the height gauge and we set it for 88 thousandths. And this is a carbide tip. Again, steel won't do. We go in there and we scratch the line around, and we flop it, and we scratch the other line around. And there's a little set of railroad tracks going right down the middle of this chunk of steel that'll tell us when to stop grinding when we get to the grinding machine. Now we're going to grind these little leading edge angles and come right to these layout lines we just put on the surface plate. And the reason for this angle is so that we'll have a warning when we get to the regular bevel grinding. We'll have a warning of how much is left to take off. And the other reason for this entry angle, which is rather abrupt, 45, 56 degrees, because when we start grinding the major edge, the blade bevels, we'll use a brand new belt with fresh standing grit. If we just grind with that belt against this edge, we strip off a lot of that grit before the belt gets a chance to work. Now, we have both sides done the same way. We're now ready to go to the next step on the blade itself. We'll be grinding the major blade bevels. We've come away from the grinding room to take a step here that's very important that we do now, and that is to roll the radius at the bottom of the ricasso, and we do it with a file. We simply get in here and file a radius on here. Okay. Now we're going to use a radius gauge. This particular one's 5/64, and we're going to check the curve we just put on there, and that's a pretty good match. The reason we use a 5/64 radius gauge is because you double that to get a diameter, which equals 5/32, and that's the size of the end mill that we're going to cut the nickel silver guard that slips right down on here. We're going to brighten up the sides of this knife, especially in the ricasso. we've got good, clean, sound steel to mount the guard on. You start out with about a 120 grit belt here, but then you want to finish up with a much finer belt and take those deep scratches out. All right, what we're going to do now is hollow grind the tang on both sides a little bit to take most of the meat off so that we don't have so much stock to take off when we go to the platen, because that's a very severe operation. You got the 8-inch wheel on here this time, don't you? Okay. All right, that's looking good. We've got a nice hollow grind there, and it flares out good here on both sides. And we're down to our layout lines at the heel of the blade, so I think we're ready to go to the flat platen now. What Jim is doing is grinding both sides of this tang to a 2-plane and establishing the taper that we'll basically be building that hammer on later, that handle on. Now, the reason for tapering the tang in this shop is to put the center of gravity of the knife in the center of the blade rather than having it be so butt heavy as it would be if all that steel were left at the back end. This way we've taken a lot of steel out of the back and we've taken a lot of the steel out of the front. When we get our master bevels ground, we've got a very nice, light, lively knife. In the past, we've always ground these bevels freehand, but not too long ago we started using a base support, this platen here, to hold the blade up while we force it into the curve of the grinding wheel. It gives us a better initial control to set up the first hollow, and that's the important hollow. So go ahead, Jim, turn it on. Now that blade gets quite hot while he's grinding it. You have to stop every few strokes and get it in the water, because the blade gets hot enough to burn your fingers. You'll lose control of your grind and ruin the blade. There you go. You can see how we're developing the first hollow. Getting a little bit thin. Attaboy. And once you get your hollow established on the straight part of the blade, you can follow it right around to the point, as he's doing now. At this point, we're putting on a 120 grit belt to start smoothing up that rough bevel. Because ultimately, when this thing's ready to go to heat treat, it'll be a very smooth blade. But you don't want to heat treat it the way it is now, because these grind lines are very deep. You wouldn't dare put that into heat treat as it is. You remember what I said about a sharp burr edge? You see that edge right there? It's like a very rough razor. and if you handle it carelessly, you can really get hurt by it. Now we're going to the 120 grit belt to clean up that bevel. We've taken away the work support, so now it's all freehand work. You notice he's got his wrists in against his body. The reason for that is if he's out there, the belt will jerk it down and ruin the bevel. You've got to be able to support and control the way you're holding the blade on the wheel. You'll also notice we've slowed the grinder down so it's not going so fast. The general rule is, as you go toward the finish work, you slow your grinder down as you get successively finer belts. We start with a 60 grit belt, and we'll actually end up at the very end of the process with a belt called the 15 micron. But our steps are 60 grit, 120 grit, 220 grit, 320 grit, 400 grit, and 500 grit. We'll use about 8 different grit sizes on this belt. The finer the belt, the slower you want the grinding wheel to go. That's looking more and more like a knife blade now. We've gone to a 320 grit belt to eliminate the 220 grit scratches, which we use to eliminate the 60 grit scratches. As we go down in grit size, we get a finer and finer finish on those blade bevels. You'll notice that these belts are running on open pulleys and wheels. There are no guards on the belt line. Ideally, to be totally safe for any given setup, you should have your belt line very well guarded and only the face of the wheel accessible. But the fact is, we use so many different belt geometries, so many different ways of running these belts that we keep open belt lines. But that's an invitation to trouble in the one-man shop where the fellow doesn't know what he's doing. OSHA would never pass this way of doing things. The blade's looking better and better and smoother all the time. In this shop, we use the tapered Tang form of blade, the tapered full Tang, and of course we grind a full blade bevel instead of a half bevel. The object is to have no more weight in the hand than necessary when you're actually using the knife, but still have all the strength you need. The strength we need comes about because of the steel structure we're using and the way we grind it and shape it. What we're going to do now is fit the guard to the ground blade, and we do that prior to heat treat. Now this actually measures 0.196 thickness across the ricasso, and this guard's been pre-cut but undercut, and it's only about 192. So we're going to go into the milling machine, the little 6/8 mill, clamp it in place, and pick up this dimension we want. And we're going to gradually come to size. You don't take off a lot at a time, because one thing that's important to remember in this line of work, once you take it off, you can't put it back on. So we nibble away at it to be sure to come to size. Nothing wrong job. What we're going to do now, this blade's ready to go to heat treatment except for one thing. We're going to install the guard, or some people call it the hilt. We'll put it right up and through the bottom of the ricasso, seat it in place, and clamp it so that it's very secure and can't slip. We put it in the vise, and we're going to drill a hole. Yeah, that looks good. We've drilled the hilt pin holes, but now we're going to do one more thing. And I want to say here that the essence of success in the mechanical arts is predictability. You want to know how it's going to work out before you do it. Otherwise, your successes are just accidental, and we don't like accidental successes because we can't always duplicate them. So these two drill holes are now going to be reamed to a precision size. Now, we've got two precision holes that'll take our hilt pins exactly and precisely with no slop. Well, we reamed the holes to a precision size, and now check and see if we picked the right reamer. If you picked the wrong reamer, yeah, that's pretty good. Well, what do you know? Huh. Things are going pretty good today here. All right, that's looking pretty good. Okay. Now, the guard, or hilt as they call it, is in place and pinned in place so it can't shift. So now we're ready to make our finger cutout. For that, we go to the big Bridgeport mill. We've got that guard pinned in place. Now you'll notice that after we set the guard in place on the blade and we clamped it up, the clamp has been on all the time since. We've not unclamped it. Now we're going to make the finger cut. Yeah, that's looking good. Now we just made that finger cut. Looked like it turned out pretty good. I think we're going to be able to save this job. At least I hope so. We ain't going to make any money this week. Yeah. That's at least as good a job as they do down in the high rent district. All right, we've got it drilled, we've got it reamed, we've got it pinned, and we've got the finger cut made. Now, one last thing we need to do to this thing before we send it out for heat treat. Otherwise, things can be very confusing. What we're going to do is number this set. And here's an interesting little number. A 6 there and a 6 there. Now we'll go to the other number. The other number there, the other number there. That way I'll never forget this knife. Now, the guard and the hilt are numbered together. We got to unpin it. And there they are, the two parts mated and fitted together with some degree of precision, each of them numbered the same, and this knife is ready for heat treat. Now, because this kind of steel is a fairly complex high carbon, high chrome, high manganese tool steel, it's not the sort of a thing that you can stick in a microwave, nor can you put in a acetylene torch on it and just bring it up red hot and dip it in the nearest can of motor oil. This is heat treated in what we call a gaseous furnace, where all the oxygen in the furnace chamber is purged so that steel can't decarburize while it's being brought up to heat. And it gets pretty hot. It has to be brought up to around 1975 degrees and held for something like 10 or 12 minutes, and then gas quenched, which simply means that the furnace suddenly has a great deal of nitrogen under pressure admitted to the furnace, and that quenches the steel and hardens it. At that point, it has to be chilled down to room temperature, and then it's put into a deep sub-zero chamber where it's taken down to about minus 200 degrees, depending on the shop you're using. At that point, theoretically, you've gotten all the martensite structure you're going to get out of this piece of tool steel. Now you pick it, you take it out of that deep sub-zero and you put it into another draw furnace at 975 degrees for 2 hours. After the 2 hours, you take it out, you let it cool down to room temperature, then you put it right back in that draw furnace, bring it up to 975 for another 2 hours. Now this is the very famous, among heat treaters and tool makers, it's the very famous 2+2 tempering draw that almost all high-speed steels get. It's one of the reasons why we get such great performance out of this particular alloy grade for a working field knife. There is no other alloy grade that'll work quite as well as this does for most of us. Well, that looks pretty good. Jim, come here. What do you think of this? Think we can save it?
Yeah, it looks good to me.
I think we might even make $1 or $2 off of it if we can find a customer.
Good.
If we don't, I can always put it in the house for a collection, or you can steal it and take it home. You know, we can do something.
Retirement fund.
Yeah, retirement fund. That's the typical and classic Loveless dropped hunter, than which there ain't no better.
Right.
As you kept telling me all these years. Good knife. Really good knife. Yeah. Matter of fact, it's the first deer hunter's knife that was truly designed specifically for that kind of work. Been very successful for us. And this is what the same thing looks like after heat treat. You'll notice it's a sort of a dark, very dark gray, purple, almost a black color. But aside from that, the geometry is the same, the shape's the same. Now the difference is this is soft steel. This is 60 Rockwell steel. This steel has been heat treated. It's hard. You could wrap some kind of a handle on this thing, put a cutting edge on it, go out and work it all day. That we don't, but you could. Whereas this steel is useless as a working tool. But that's the difference. The shape is there. Guards have been installed. Everything's the same except for the condition of the steel. One is soft and one is hard. Now we're ready to go ahead and finish off this heat-treated blade, polish it out, get the guard soldered in place, and then finally we come to the building of the handle. Now Jim's got a fresh new 400 grit belt on the grinder. It's going pretty slow, and what he's doing is getting back to clean steel from that color that left over from heat treat. See how that's brightening up? This is the beginning of the process of finishing off the blade prior to assembly. We're starting with 400, and then we'll go to an 800 grit belt and a 15 micron belt, and then we'll go to the buffing machine where we really put the glaze finish, or the so-called mirror polish, on the blade. Now, all through this process, we have not had the fan and the vacuum on. Now's a good time. I'm going to put the finely ground blade onto the polishing lathe now and show you how we come up to the mirror finish. This is the roughing wheel, and it's quite aggressive. From this roughing wheel, which has a stainless steel compound, we're going to go to the green chrome. The object here is to be able to come out like, almost like a mirror. You'll note that again, we're below the center line of the wheel. So if the wheel were to catch the blade, it would take it away from us. This is very hazardous work. I've got my wrist hard against my body to control that blade against the polishing wheel. And if we've done it right, we end up with this. And it's at this point where, if you haven't done all the preceding steps carefully, you might find some deep scratches in there, maybe even from back at the 60 grit stage. And if you do, you've got to go all the way back to the beginning and do it all over again. We've got pretty much of a mirror, as you can see, the way this thing handles the light. It's a brilliant high polish. What Jim is doing now is washing the blade. And here's why. You'll notice that the last thing I did on the buffing wheel was use a green chrome wheel to pull up the mirror shine. But the problem with that is that it leaves a very, very thin coating of a wax on the blade that will inhibit a good solder joint. So we wash this thing with a mild detergent solution very carefully. So now this blade is clean and it's ready to solder. And that's going to be our next step. We're going to install the guard on this blade that we polished a little while ago and get it ready for soldering. Of course, we very carefully drilled and reamed those holes before heat treat and fitted the guard before heat treat, and now everything fits up real nice. But it's not ready for soldering yet because it's got to be closed up a little bit. And to do that, we're going to actually peen these pins in place here on the bench block. The bench block is a section of 132-pound standard mainline railway track that's been cut off, and I've machined one end, and we use this curved end. It's a very fine piece of equipment. We're using, by the way, a very smooth-faced hammer. It's only kept, the reason why the handle is red, that means it's a very special hammer. It's only used for this particular job. As we peen these pins down, we're closing up the gap so that when we solder, we'll have a very close, tight fit. The pins are exactly the same material as the guard itself, that is to say 30% nickel silver, and they're very malleable. They do a very good job of riveting down. Okay, that looks pretty good. Yeah. Okay. We're going to solder the guard on now that we've assembled it and pinched it down with the pins. We're going to solder it. I've prepared the electric soldering iron with a special nose piece on it, and now I'm applying flux around the guard. This nose piece has been machined to just take the Tang thickness, and we put it down with the Tang into the fixture with a blade up. Now we start applying the solder. And we solder around those pins that we peened over to be sure there's not going to be any unsightly gaps. And we start flowing the solder along this joint face. Now the object of this is to have a totally saturated joint with a very smooth finish line visually after the handle's assembled. We're using a solder that is not a lead tin solder. It's a bismuth alloy made by eutectic alloys. And it flows at a good deal higher temperature than the regular lead tin solder. This particular solder is used when they assemble food processing lines, stainless steel food processing lines. For instance, the New York Board of Health approves this solder because there's no lead in it to leach out and transform to arsenic. What we like about it in the knife business is that it stays bright. It doesn't go dull like a lead tin solder. Very good, Robert. Only been doing this for so many years. But we got a total saturation all the way through that joint. In other words, we've got a good solder joint here because we've got lead coming out the back end. That means it's a totally saturated joint, and thus it's a weatherproof joint, and it'll survive as long as a knife will survive. We're going to, now that we've got this thing beautifully soldered, we're going to take off this surplus solder on the rear surface of the guard and on the Tang to get it ready for precision handle pieces so that we really got a tight fit. We used to do this with a file years ago. It was a very tedious job, and you couldn't really keep it straight very well. There was always a little bit of fall off on the ends. So we developed this technique several years ago, and it's been very successful. The object, of course, is when we put that handle material on there and glue it all up with epoxy and everything, you want the handle to be perfectly matched to the rear surface of the guard. And the way we do this is with a milling machine. You have to come down and this is a little carbide end mill, and you have to come down and barely touch the Tang. If you hit too hard, you're going to gouge it and ruin the job. That noise you hear is the bottom of the cutter just touching the Tang. The carbide cutter, which is a very expensive piece of gear, but nothing does it quite as well. We have a true plane on the rear surface of the guard that'll match a true plane that I'm going to make on the handle material. And we've come down and contacted the Tang so that all that surplus solder is now gone. You can see that it's not there anymore. We've got true, straight, flat metal surfaces. And this is the only way I know to do this job. You can't do it as well with a hand file. It can be done, but not as well. Now, I just about got this knife ready to start putting a handle on. Now we're going to do one last thing to this knife blade before we start building the Tang. We're going to sandblast and clean up the Tang. Now there's two reasons for it. One is, of course, to get it clean so that we don't change the behavior of the epoxy adhesive. And the other thing is that the other reason is to give that epoxy adhesive a very tight, firm grip on the surface, because Tang sandblasting it roughens it up. It makes it almost impossible to remove the handle slabs without literally destroying them. Now we've got a very smooth and slightly rough surface on these planes that the epoxy will bite very good. There's no other way to do it than with a sandblaster. I used to try to rough these surfaces up on a sharp burr on the polishing lathe, but that didn't do the same thing. This is the greatest improvement in handle construction we've made in this shop in the last 6 or 8 years. Now, once this tang is sandblasted, it shouldn't be touched with any greasy hands or anything because it's, in fact, mechanically and surgically clean. And that's what the sandblasting does. Of course, you've got to be very careful with your sandblast cabinet to keep it away from your precision machinery, because if you don't, the grit will migrate, and the next thing you know, you're in trouble with your good stuff. That's why it's here where all the grit is anyway. Good job. Now we're going to build a handle on this knife. What we're going to do now is prepare these 2 pieces of green canvas micarta to precisely fit the tang and the rear of the guard. Now this fixture gives us both angles at the same time. This plane is at about 3/4 or to almost a degree of incline, and then the divergence is on the pins. So when we come off of here, these handle pieces will go right against that knife blade, that tang, in a perfect fit. This is another little thing we worked up here several years ago. We used to do it on the platen of a belt grinder and then clean up with a file. When we do it this way, we don't have any cleanup to make. We've got perfectly sanitary, clean, sharp. And there we are, perfectly machined surfaces to go onto the tapered tang and match up to the back face of the guard. There isn't any other way to do this as precisely and nicely as you can do it on a milling machine with a proper fixture. Now we're ready to fit the handle materials. I've prepared the red liners, and we've got the green canvas pieces we just took off the milling machine cut. And we put it up into the tang and fit it very tightly and closely. And then we clamp it very firmly in place. And you check for fit. And that's a good fit. This isn't going to be a good knife, it's going to be a great knife. Now, notice that we're making this handle out of green canvas micarta. The most traditional handle material for a hunting knife in the American market is stag. 150 years ago, we used the horns of domestic animals, but in the last 20 years, we've been using the horns of the sambar animal from India. They drop those horns on the plains of northern India every year. You don't kill the animal to get the horn. They just drop it like our own animals do. And companies import this stuff, and so we have to make a lot of stag handles. The Japanese market is very, very demanding of stag. The European market, on the other hand, they don't like stag. They want micarta, such as this material. Whenever a customer asks me to build him a knife and he wants the very best handle material, the very best quality I can put on the knife, there's only one answer: this green canvas micarta. On the other hand, some customers say, "Bob, please make me a knife and give me some good stag for the handle." Then I always say, well, why do you want a second-class handle material on a first-class knife? Because, in fact, that's what it is. There's no stag or animal horn or hardwood in the world that will give you a lifetime of service that this material will. It's in fact the best thing we can put on a knife. It is not visually pleasing to many people, but it is to me and to a few other people. I've got customers that won't have anything but green canvas. And that's all I want on my own personal knives. Now we're going to drill this half handle assembly that we've got clamped up. It's very tightly fitted. We're going to drill it to take the handle fasteners and the thong tube. Now we're going to pin these holes off so that this handle plate can't possibly shift in the clamp up while we drill this other big hole. By the way, you'll notice that each of these little drill presses has its own individual little 60-watt lamp shining right on the drill point. The overall shop lighting is large 8-foot twin fluorescent fixtures, and it gives us a very good overall light level, probably as good as you'll find in most shops. But we still like some very small direct lights on our work sites to help us see precisely and exactly what we're doing. If there is any typical failure of a shop craftsman, it's his vision over the years. It'll get worse and worse if he doesn't take care of it. If you've got enough light, that helps. Now we're drilling the thong tube rough hole. Now that handle is drilled in place and it can't move. Our next step will be to saw the surplus material away and then grind some more. Then we'll have to turn it around and do the same thing to the opposite side. It's going to be a great knife, no question about it. Now we've got this thing drilled and pinned off so that the handle material can't shift. But now we're going to trim off this surplus material on the bandsaw. Before I start, I want to warn you that this is the most hazardous machine in the shop. If you handle it carelessly, you're going to leave pieces of yourself on the table when you walk away, and it will smart some. Not to mention the fact if you lose your critical members, you know, like the apes, we have opposing thumbs, and these digits are very important. If you lose them, you can't work no more. A couple things more to say. One thing that's very important when you're dealing with a bandsaw, I'm sure some of you have noticed this, is when the blade gets dull, you got to push harder, and that's dangerous. You want to stand at the saw erectly, and you don't want to be leaning into it. You want to be in control of the work you're feeding through the blade all the time. You notice these two pins sticking up, they're my handhold for feeding this job. I'm not pushing with my hands in alignment with the blade. They're well off to one side. Because as you finish your cut and break through, inevitably, it jumps forward a little bit. we've cut away all the surplus handle material to within about a 1/16 of an inch of the steel of the Tang itself. Because that's all surplus. It's not on the finished knife. The next operation is we're going to go into the grinder, and we're going to take a little bit more off. Come very close to that steel outline with a little bit of a slant on it, and that'll make a very neat job when we go to the epoxy. Now we're just going to clean up a little bit more of this surface material and then give it a little bit of a slant that'll just naturally lead into the handle profiles. Turn those things on, darling. Now, if you can follow, I'm going to step to my right about 48 inches. Okie doke. Well, now we're going to take this handle off, just punch out these pins, and we'll go ahead and do the same thing to the other side that we just did to this side, starting with the initial clamp up, the drilling, the bandsaw job, everything exactly the same but in a mirror image. The red fiber material is nothing more than a little personal vanity of my own. I've always liked girls that had a little bit of lipstick on them. And I think red is a very exciting color. It's an up color. So we put red fiber between our handle material and the Tang. And it has another true function, especially with stag handles, in that it's very compatible with the epoxy. And stag has a natural wax content in it where it doesn't like to stick to the epoxy nearly as well as it will to the red fiber. So we use the red fiber as an additional adhesive element in the sandwich structure. Now, I've got some white fiber and I got some black fiber. And I've had customers ask me to put in black or white liners. And I say, nope, the Loveless knife has a red liner. It always has and it always will. I happen to like red fiber. And basically, I make these knives to please myself. Now, I'm very gratified if it pleases everybody else, but basically, it's me I've got to please. And I just like red on my knife. Something like the red insert on the front sight of a pistol. We use a particular form of handle fastener that I designed years ago. It's not the ordinary cutlery rivet. In fact, it's an 832 flathead machine screw, and under the head of it we use a brass bush in this case, and on the bottom end we use a brass nut. They have to be installed to precise dimensioning depths, the countersink to precise dimensioning depths in the handle plates, or the handle form won't come out. Now, we've learned over the years what, for various model knives, what depth we need. And I made up this little setting plate some years ago, and in this case, for the 4-inch dropped hunter, we're going to use a critical depth from the back to the top of the counter, the top of the nut, of 197 thousandths, and that's what I've set the depth of the countersink at, 197 thousandths. No, I'm wrong. We're going to use 212. excuse me all the hell. Now, we're going to countersink the front holes. But we want the rear part of the knife to be slightly thicker from front to back than the front side, so we put in a spacer that'll keep the countersink from going quite as deep on these rear holes. Now these handle parts are just about ready for epoxy assembly. All right. Get these out of the way for a minute, and we're going to mix our epoxy. Now, this epoxy is pretty common stuff. This particular brand happens to be Conap, and only because it works well. And it's not at all critical for mixing ratio. The base resin has a big hole in the tube. The hardener has a little hole in the tube, and you just squeeze out equal lengths. And I'm not sure what we knife makers did before we had epoxy. I guess we used something, but anyway. This is miracle stuff. Mix it up. We've got about a 20-minute pot life for this material, so you can't mix it and then go in and have lunch. You've got to stay here and put the knife together. And we're going to start. We're coating the near side of the tang, or what the collector boys call the obverse side. I've never been able to figure out why they do it, but I just say the near side. We coat it up good. Then we grab the piece of red fiber that I've already marked in for near side. We put it down on it. Now, we coat the fiber. This is nothing but a common ordinary soldering brush that's been cut off a little bit to make it more manageable. We cover this whole surface with the mixed epoxy. And then the near side handle goes on there. And at this point, we install our fasteners, push them down through that hole. Now we unclamp this and just turn it over. And this horizontal vise, by the way, is one of our secret weapons around this shop. Now we'll put the far side red fiber in place. And put some more epoxy on. Be sure that you get plenty of epoxy up behind the guard, all the way around both screws and the thong tube. And we put the far side handle piece on. And we run a couple of nuts down there. I've already checked these nuts to be sure that the threads are good and they're free running. Now we take it out, turn it back over again so the near side's facing us. And I reach up and get another one of my favorite tools, a power screwdriver. Now, you can set various degrees of torque on this thing, but we don't have it set up to maximum torque, because if you really squeeze too hard with a screwdriver, you'll squeeze all the epoxy out of your sandwich, and then it won't work. But you'll notice that we have epoxy coming out all the way around both sides of the handle material. That means we've got a good epoxy job. You don't have to do this, but I do it. It's just less to take off when it hardens up and we go back into the grinding room to shape this handle. And there's our knife ready, and we'll just wait for it to get hard, and then we'll shape the handle. The knives we make are very simple. They're almost classically so. They exhibit an economy of line. There are no protuberances. There's nothing superfluous about the Loveless knife design. It's very pure, supremely functional, and in its way, it's very restrained. They're just very neat. They look right. They look right to me, and practice has shown over the past 30 years that they look right to a lot of the world, or a lot of knife users. I can't explain quite how I get there, except that, for instance, the Dropped Hunter, which is the most famous knife in the shop, has gone through about 7 generations of design, each time being refined more and more in a minimalist way. The very earliest Dropped Hunters were nowhere near as functional and neat as they are now. It's taken time to get there, but then, of course, it's taken time for me to mature my own views of cutlery design, too. The mirror finish is a primary requirement if you're trying to achieve corrosion resistance, a maximum amount of corrosion resistance, or, as we say down on the street, resistance to rusting. And you have to have a mirror finish, a super finish, a very absolutely smooth, highly polished finish. Because any place there's a rough part, microscopically, there's a little rough scratch or something, the active corrosive agents, and they are even in the air, can attack those little rough grooves, and that's where corrosion can start. Once it starts, of course, it grows. These are not truly rust-proof knives. They are rust-resistant knives. We get it from the technology, we get it from the alloy itself. Any steel, any tool steel, it's got 14, 16, 18% chrome, is going to be essentially corrosion resistant. Way back in the Delaware days, I used Jessup's 139B with 2.5% nickel. That was very hard to rust, too. But this stuff is so much better than anything we've had in the past that it's just incomparable. 20 years ago, if you asked the average knife user, would he want a stainless knife or a carbon steel knife? Oh, I want a carbon steel knife. I can keep them sharp. Well, those days are long gone. These steels that we use now, primarily the ATS-34, the 154CM, BG-42, they are, to all intents and purposes, rust-proof, with a very minimum amount of care. That's the reason for the brilliant shine that we work so hard to get here in the grinding room and on the buffing. As for the hollow grinding, there are, of course, 2 major ways to grind a knife, either hollow grinding or flat grinding. The problem with the flat ground knife is that after years and years of being in the field and being sharpened many, many times, each time it sharpens, it gets an increasingly blunter cutting edge. The hollow grind knife, on the other hand, can be ground over years of time, halfway up the blade, and you're still within thin steel, and you can still achieve a sharp cutting edge. You can't do that with a flat ground knife. Flat ground knife ends up like a bloody coal chisel. A choil on a well-designed knife is a total waste of good, useful blade surface. A choil, of course, is this big cutout right ahead of the, at the lower part of the blade, ahead of the guard. And some traditional makers in this country used a big choil so they could put their finger ahead of the guard and choke the knife. Well, when you have to do that, you've made the damn knife too long anyway. Aside from that, in use, the point of maximum leverage in the cutting edge is the cutting edge that's closest to the guard, where you have maximum leverage coming down on the job. For instance, cutting tent pegs or starting firewood or something like that. I find no need for a choil. Visually, they're very disruptive, and technically, they can be a weakening point in the blade, too. We've got this thing. Several hours ago, we epoxied this up. The epoxy is now cured, and it's hard, and we're about ready to start shaping the handle. You're going to hear some noise because this generates a lot of smoke and flames, so we're going to turn on the vacuum and the fan now. Now we've got the rough shape of the curves cut into the handle with the big rough belt machine. Now we're going to smooth this thing up and make it feel better. We're going to do it with this thing. This is a flexible belt. It's not backed up, and these wheels are rounded a little bit, so it gives the belt a curvature, which helps us actually shape the concave surfaces of our handle. Symmetry. We're looking for symmetry. Both sides of the knife, the vertical center line, both sides of the knife have to be an image of the other side. Each side has to be an image of the other side. In other words, we want a symmetrical knife handle, If we knew that every knife was going to be used by right-handed people, we could make it a certain way, but we don't have any control over that, so we have to make it so that it's useful to anybody. Plus which, it's just pleasing that way, because the human spirit has a natural urge to achieve symmetry. And that's what we work for in this position. Now, we roughed it in over there, we pretty much finished the shaping here. Now it's a matter of polishing out and getting it ready for the trademark and the leatherwork in the sheath. This steel must be mirror polished to give its best corrosion resistance. All stainless steels need a very, very finely polished surface to be the most corrosion resistant, or as some people would say, rust proof. That's not really true. But when they're highly polished, they're very corrosion resistant, whereas if they were less scratchy and everything, corrosion could get a bite. That's one of the reasons we put a mirror polish on these Loveless knife blades. When we're finished with this object, they'll go out and give somebody 200 or 300 years of service if they know how to do it. And there isn't a better deer hunter's knife in the bloody world than this one. It's exactly and precisely what it needs to be, and nothing less and nothing more. I don't know how to do any better than this. Well, we got this knife all finished, and the last thing we do is we want to put a trademark on it. And this is the way we do it. We got the machine hooked up. The ground wire goes to the blade. The power wire goes to this stencil holder with a wet cotton surface, and we got the stencil taped onto the blade. We go down on this for about a second or two, come off and let it degas. Another couple of seconds and degas. We do that 4 times. Each time we're burning it deeper. Then we reverse polarity from DC to AC, and that will darken the bottom of the etch. About 3 or 4 seconds, take it off, unclip the ground, and now we have a trademark. Now, the way we make a sheath for this knife, of course, we've cut it out to a pattern, folded over the back flap and stitched it down. This, of course, will make our belt loop. But now we've got to get it into hot water and get it pretty wet so that we can actually wet mold it around the knife. And so one property that leather has that no other substance has, and it's why leather, the hide of a cow, is, as far as I know, absolutely irreplaceable. We set it down in there about like that. We hold it shut, and we, with our thumb, we press it into the leather, push the leather down around the knife. Now this is called the wet molding process. And it's the only way there is to get a really good, special, custom, snug fit for the knife you're putting a sheath around. These knives, although they're very, very closely alike, they are not interchangeable. And when we open it up, we'll see the line of the blade on the back side and the front side of that sheath. And there's the reverse pattern of the handle. And the other thing we need is on the back flap, down at the bottom of the blade pocket, a couple of drain holes. So that if you happen to be wearing your knife and you're crossing a creek in northern Colorado mountains, trying to chase down a mule deer or an elk, and you fall and slip and fall into the creek, you get water all over everything. When you stand up, the water will drain out of your sheath instead of just sitting there and rusting the blade, or otherwise messing things up. Now it's wet molded, and we've already cut a welt to fit that blade. Now, the way the welt fits, the knife's put into the sheath, it's held slightly open, The welt fits in there very snugly. When you close that up and stitch it up, you've got the Loveless snap fit sheath. And that's all there is to it. I'm going to have to wait for that to dry, and then we can cement it in and stitch it in. The finished job looks like this, with this very knife. You can hear that little click. That means that the point of the guard has gone past the internal cam of the welt into its home position. I don't like keeper straps on leather, on knife sheaths especially, so I came to this wet form pouch design many years ago, and I've never had reason to change it. It literally is the best there is. Even if you happen to go upside down off your horse on a shale slide on that mountainside, that knife's not going to come out of the sheath. It's made of 8 to 9 ounce backs, cowhide backs, the very best grade of leather I can buy, runs about $5 or so a pound. And then a very heavy piece of sole leather, which is exactly the same kind of leather the shoemaker would half sole your shoes out of, down inside the two halves of the sheath clamshell. And that structure is stitched up, and it becomes very thick and strong and rigid, so that you now have a safe sheath to keep your knife in. There's nothing flimsy about a Loveless knife sheath. Probably one of my greatest criticisms of most factory knives is that the sheaths are miserable. But ours aren't, and that's the end product. And I'm also pretty proud to put my name on it, too. And once a sheath is made like this, it should give you 25 or 30 years of service, perfectly good service, without having any problems at all. Unless you use a lot of soft, wet saddle soap, in which case it'll limber up. Satisfaction is in making a useful tool, a tool that can be perceived by many men to be of obvious high quality, and having been able to do that from the most pedestrian of raw materials, a steel bar and chunks of other stuff and some micarta and maybe some cowhide and so forth, and you end up with such a magnificent tool. It has a unity, it has a purpose, it has some honor, and it has my name on it. And if you want to call that egotism, then so be it. I tried to get along with my fellow man, but I won't compromise my knife making. This is living creatively, making something out of nothing is the biggest kick in the world. There's nothing like it. I don't care what kind of drugs you want to talk about, what kind of whiskey you want to drink, what kind of sex you want to play with. There's nothing, absolutely nothing that comes that gives you this tremendous high of creating something out of your hands and your mind and your hand-eye coordination with your shop tools. Sure, it's not pleasant. You've got to eat a lot of grit. Those of us who've done it over the years, hell, is probably going to accelerate our dying. But I don't really care about that. I'm going to leave behind me a hell of a good body of work. And I can see where 200 or 300 years from now, if this society still exists, there are going to be men who will have Loveless knives and who will like them and use them, value them, and that's good enough for me. I don't need anything more than that.